Hi, I am Bob Rathall. I am self-publishing this paper. It's entitled Superfluid Helium Type II Superconductors and Disorder. So I have been thinking about this subject for a long time. I have a simple physical explanation of superfluid helium, and the physical model has implications for a physical model of type II superconductors. They are linked. And I've constructed this model to give me some intuitive insight into the actual structures of these materials, the physical causation. So I have my BS in physics and PhD in experimental physics, and I did a thesis involving a liquid helium Dewar flask and a large magnet. I grew my own crystals and worried about lattice irregularities. I became interested in the disordered Hamiltonian because of growing my own crystals. And I am an enemy of Hilbert space. That requires a little bit of explanation. Hilbert space removes physical insight into the actual problem, even though it might be a very useful tool for calculation. So I think you need to have some kind of physical insight. Oddly enough, Penrose and I sort of agree on this subject, that we need physical insight into the problem. All right, as they say, let's jump right into it. Intuitive view of superfluidity and an intuitive view of superfluidity and the two-fluid model. First of all, from first principles, we know that in quantum systems, the net mass or probability flow at a point is given by the flux vector is the probability density times the gradient grad of the probability, where psi is the wave function, of course. A long time ago, I had a reference to a paper that showed that disordered Hamiltonians produce localization in the wave function. I think this is sort of an intuitive idea. It's intuitive to me. We'll try to explore what the implications of that observation are. And we will make a further assumption that the solutions to disordered Hamiltonians are random functions. This is really important. Talk a little bit about random functions. We know that random functions are self-orthogonal under translation. So if psi 0 is a solution to a disordered Hamiltonian, then the some translation vector times psi 0 are orthogonal if the translation vector operator length is substantially greater than the correlation length, where psi 0 is the 0th order random function solution. Then all the solutions to the Hamiltonian are simply translations operating on one solution. So here, this is the many-body wave function. And so if you take the translation vectors and multiply it by one of the functions, then that gives you all the complete set of solutions, because they are orthogonal to the random Hamiltonian, disordered Hamiltonian, that is to say. So and Tn are generalized multiples of the correlation length. So so they can be rotationally separated. They can be by length. There are probably many ways that you can make them generalized translation vectors, translation operators. So we also know that for random variables that psi and grad psi are independent. So then localization becomes the minimization of the flux around a physical surface. Call it localization L. So the localization is just the integral of the flux around a closed volume surface. So that would be call that a localization function. We can signify this by asserting that the interior of the integral has some sort of localization when, if you say the rate of change of localization by some change in boundary equals 0, where the boundary is some type of morphological geometric exteriority. That's a mouthful. Application to a liquid. So the ultimate dense disordered system would seem to be a fluid. This model would suggest a fluid consists of fuzzy localizations. I think this is generally experimentally seen in correlation lengths in liquids. Application to liquid helium. Liquid helium is then presumed to be a collection of fuzzy balls as a result of this localization. The great superfluid transition happens when all the balls become equal in size. Here we have a set of localizations of unequal size, and the transition is when they all become equal in size. And it so happens that there is a drop in the density of helium at the transition temperature caused by a reduction in packing density. You can see the packing density is not as good here as it is here. I don't have these are all 40-year-old references, so I can't tell you one, but it was observed. The uniform localizations have the lowest energy. So this leads to the two-fluid model proposed by Feynman et al. The normal fluid component is the fuzzy balls found in all fluids. The superfluid is a quasi-particle state existing upon the fuzzy balls, which are all the same size. Equal size is a requirement to remove extended randomness. So it allows the quasi-particles to extend over the entire length of the fluid. So the quasi-particle state depends on the substantial uniformity of the fuzzy balls to remove what would be called scattering. So I think that was kind of interesting that I managed to find a physical explanation of the Feynman two-fluid model of liquid helium, it's very visual and very simple. The fuzzy balls all becoming uniform in size. So relationship to type 2 superconductivity. If localization makes superfluid helium, then probably localization produces type 2 superconductivity. Type 2 superconductivity exists largely in copper oxide crystals. Well, copper oxide with a whole bunch of other things, where conductivity occurs in planes within the crystal structure. Current flow is thus generally two-dimensional. And because crystals are by nature hard to grow without some disorder. The crystal structure is in my opinion disordered. This promotes the creation of localizations, where here L is the measure of localization. But see here, it's a two-dimensional L around a closed two-dimensional it's a two-dimensional surface. So here the integral is a closed two-dimensional path. In this geometry, is much easier to create highly localized electronic density functions. And if you only have to make a two-dimensional path to create a localization. So it is proposed that when temperature is low enough, it allows quasi-particle formation on these localizations, similar to the quasi-particles in the helium case. The electrons in this conduction mode will have little interaction with the underlying crystal structure, being basically density waves existing on the localizations. It is likely that these particles might be similar to Cooper pair bosons. Cooper pairs are needed to avoid scattering interactions with the bulk crystal structure in which they exist. They are also the lowest energy level within the bulk structure. Because this in type 2 superconductors, because the two-dimensional structure is much smaller than the extended superconductor quasi-particle wavelengths, it can be argued that the superconductor carriers might also be fermions. It's probably unlikely. Type 2 superconductors do not have the typical Meissner effect. The Meissner effect requires bulk conduction. Type 2 superconductors exhibit vortices. This could be explained by the two-dimensional nature of the conductor. The conductive sheets might exhibit multiply connected regions in 2 dimensions. This could allow for the existence of vortices. This would also allow for the localized minimization of electromagnetic free energy. Just to add a little justification to this, these are 2 references I discovered recently. The disorder-induced transition from type 1 to type 2 superconductivity in the Dirac semi-metal palladium telluride, and enhanced superconductivity in titanium manganese alloys through manganese doping. So here you are changing the manganese doping, which will create greater disorder or less disorder. So I think this is, I have a very interesting argument. Seems very possible. And if you have listened this far, I'm grateful. I do hope you do not judge me too critically. This is kind of a risky well, I don't know. I'm a little bit concerned that I would embarrass myself, but I think if you don't know me, I don't know you, I don't care too much. If this is a crackpot theory, at least I have used equations and physical reasoning. So I hope you've enjoyed this. Thank you very much for watching.